Hello, welcome back to Math 3321. Today we're going to be starting Chapter 3, and we're going to look at Section 3.1. So Chapter 3 is all about numeration systems and whole number operations. We're actually just going to touch on 3.1 for this unit, and then we'll do the rest of Chapter 3 in the next unit. So in this unit, you should be able to understand and explain numbers, their origins, a representation, use different use and know about different numeration systems, especially the Hindu Arabic number system, which is just our 10-digit number system that we use. And then place value and counting in base 10. This section also has a lot of information on other bases. We're not going to go over that in this course. So this should be a quite short video. All right, so numerals are defined as the symbols that are written to represent cardinal numbers, so the value of a number, how much. So these are some examples of some existing number systems. So you have Babylonian, Egyptian, you'll probably recognize Roman numerals, and then Hindu and Arabic numbers were combined to get our number system that we use today. So these are just examples of how you would count from 0 to 10 in these different number systems. You'll notice some of them don't have ways to represent 0, which is interesting. So a numeration system is a collection of properties and symbols agreed upon to represent numbers systematically. So we have a kind of informal way of counting numbers. You may represent tallying, right? So this is a tally number system where we use single strokes to represent the number counted. We typically group them by fives. So to count 13 items, I might say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then 1, 2, 3. And I can read this as 5, 5, 3, that's 13. And then if you're interested in Egyptian numerals, they often have different descriptions and Hindu Arabic equivalents. And then Babylonian numbers, they just have one value for, or one symbol for 1 and one symbol for 10. Mayans have a symbol for 1, 5, and 0. And then Roman numerals is where we're going to spend a little bit of time in this unit, just briefly. So they have symbols that represent 1, 5, 10, 50, 100, 500, and 1000. Those are the ones we're going to be interested in. So how we write Roman numerals is we start from biggest to smallest value, and we are essentially adding. So if I wanted to represent 10, it's just 1x. But if I want to represent 20, then I need x next to each other. If I want to represent 60, I would do lx. If I want to represent 600, it would be dc. Now, the trick here is that if we want to do values that are essentially one symbol less than the value it represents, then we can write them from smallest to largest. So for example, if we want to write 4, we write IV, and I is the symbol for 1, V is the symbol for 5, and since we put the smaller symbol first, we are subtracting instead of adding. So this number represents 4. This is IX, so 1 away from 10, or 1 back from 10 is 9. XL, L is 50, X is 10, so 10 away from 50 is 40. XC is 10 away from 100. CD is 100 away from 500 or 400. And CM is 100 away from 1000. So we're in the year 2024 when I'm making this video. So how could we represent 2024 in Roman numerals? 2024 is really the number, right? So to get 2000s, we could, we could have an M represents 1,000. So to get 2,000, we need 2 M's. And then to get we don't have any hundreds we need to represent, but to get 24, I need to represent 20. So that will be 2 X's for 10, 10. So 1,000 plus 1,000 plus 1,000 or plus 10 plus 10. And then to represent the 4, I need to say 1 less than 5. So to be most efficient in our symbols, instead of writing I, the appropriate way to make a 4 would be IV. So we'll do an IV. So 2024 would be MMXXIV. You'll often see the Roman numerals around the Super Bowl time because we represent the Super Bowl numbers in Roman numerals. All right, so the Hindu-Arabic numeral system is the number system that we use today. All of our digits are constructed from 10 digits, and they start at 0 and end at 9. And the place value system is based on powers of 10, the number base of the system. So we work base 10. And it's actually kind of historically relevant that we use base 10 because we have 10 fingers and 10 toes. So it's easy for us to count in groups of 10. Or in powers of 10. So place value assigns a value to the digit depending on its placement in the numeral. So when we read numbers, the leftmost digit tells us the largest place value, the rightmost digit tells us the smallest place value. So we have, if we don't have any decimal values, then the rightmost is our units, then to the left is tens, hundreds, thousands. And so you can notice that every number is representing a one larger power of 10 as we move to the left. So units is really 10 to the 0 power because anything to the 0 is equal to 1. And then our tens, so we have 7 tens in this number. So it's just 7 times 10. And then here with 6, we have 6 hundreds or 6 10 squared. Then 5 thousands, and that's 5 10 cubes. So this number is read 5,678. We can expand numbers in this formal way, and it's going to be helpful for us when we get to doing operations with these numbers. So 6,789 we can represent as 6 times 10 cubed, so 6 thousands, 7 times 10 squared, or 700s, plus 8 times 10 to the first power, 8 tens, plus 9 ones, or 10 to the 0, you could write as well. So just to practice how we would say some of these numbers, this chart expands it a little bit. So going to the left of their decimal place, we have our units and bigger than 1, and right of our decimal, we have place values that are smaller than 1. So again, as we move left of the decimal, we have our ones, tens, hundreds, thousands, 10,000s, 100,000s, and then next would be millions, and then 10 millions, 100 millions, then billions. But as we move to the right, we start with our tenths, then our hundredths, thousandths, 10,000ths, 100,000ths, and then we would have millionths as we go to the right. So we have to say the THS part of the end of that word. And so every time you move 1 to the left, you're multiplying by 10 to get your place value. So one larger power of 10, and when we move to the right a decimal, or to the right a place value, we are dividing by 10. So how would we say this number, a 2 and then a 4? That's 2 tens and 4 ones. We usually say 24. Then 2 4 0, that means 2 hundreds, 4 tens, and 0 ones. So we typically say 240. 2 4 decimal point 5. We should read that as 24 and 5 tenths. So I want you to practice using the decimal point is where we say and then the decimal we need to say in terms of our tenths, hundredths, thousandths instead of 0.5, for example. So if we go to the next one, 24 and then so this 0.5 tells me I have 0 tenths and 5 hundredths. So I could just read that as 24 and 5 hundredths. Now, this next one, 524, and we could either say 3 tenths, 2 hundredths, or 32 hundredths, because 32 in that hundredths place. So I have 32 hundredths, which is the same as 3/10 and 2/100. Now this number doesn't have a decimal, but we see that we have 5 10,000s, 2,000s, 400s, 3/10s, and 2/1. So we could read it that way, or we could say 52,432. And then lastly, we have 52,432,976. So when we think about using our powers and our place value system for powers of 10, just a quick reminder that if we have a number to a power n, so a to the power n, it means that we're multiplying a to itself n times. So 10 cubed is 10 times 10 times 10. 10 to the 5th power is 10 times 10 times 10 times 10 times 10. So we multiply 10 5 times together. If a is not equal to 0, then this definition works. But if we have the power of 0, then we as a mathematical convention say that that is equal to 1. All right, so a really useful tool for this course is going to be using base 10 blocks. So your book uses a little bit of different vocabulary than I'm used to, but they say they call a long one of these bars that has 10 unit blocks in it. A flat is a 10 by 10 flat square. And then a block is a 10 by 10 by 10 big cube. So we have a unit, a flat, or a long, a flat, and a block. I might say a small square, a bar, a flat square, and a cube, if I were to use these in my own everyday language. But we can use base 10 blocks to represent certain numbers. So I want to show you a resource that you have online, since this is an online course. If you want to practice using base 10 blocks in your own work, you can go to mathlearningcenter.org, and you'll see this one app called Number Pieces. So if you open the Number Pieces app, then it will allow you to have your flats, your longs, and they don't have a representative for the big 1000 cube, but that's just one limitation of this app. But let me see, let's delete these. The first example we were going to do is 51. So if I want to represent 51, then I need to see what's the smallest place value that I need to represent. And it's a 1. So the ones place. So what I can say is, let's let 1 unit block just be equal to our 1, our whole 1. And then in that case, these long bars are going to represent tens because they have 10 ones in them. So if I want to represent 51, I can use 5 tens and 1 unit block. So this would be a way we could represent 51. Now, the second example was 423. So again, the ones place is the smallest value I need to represent. So I can have a unit block be representing my ones place. And that means that my tens place will be my long bars, and my hundreds place will be my flat squares. So I need 400s, might run out of space here. Move my key over here. So I need 400s, 2 10s, and 3 1s. So this should represent 423. Now I want to challenge you to think about how you could represent a number that's smaller than 1. Say if we had 5 and 1/10 or 42 and 3/10 instead of these numbers that the smallest value is a unit. All right, so that's where we're going to stop this section, and you should be able to do your section 3.1 homework now. And as always, let me know if you have any questions.